Hi everybody. Today we're going to talk about Web3 scalability with Oasis Sapphire. But first, I'll start with what is scalability? Well, there are many aspects to it, and it's a common topic in systems design. So none of these are specific to Sapphire or even blockchains in general, but there are a few techniques that can be only used with Sapphire and not on transparent EVM chains like Ethereum or Polygon. In the next 20 minutes, we'll cover how to make your dApps more scalable using the unique features of confidential EVM and Oasis Sapphire. Some of the problems you'll encounter when trying to make your app more scalable are throughput, concurrency, and parallelism. And obviously, you want to decrease the latency, transaction size, the amount of bandwidth you use, and how much communication there is. As you'll see, the more mindful we are of how your dApp communicates with contracts, the types of transactions they do, and where the bottlenecks are for throughput, you'll get more insight into how to take different approaches or make design decisions which enable your dApp to run faster with less lag and with less gas usage. Let's quickly go over some basics to refresh our memories. Concurrency is where two or more tasks are all making progress at the same time. If you have one CPU with one core, your OS can still run lots of tasks, but only one task is ever running on the CPU at any point in time. So the CPU needs to switch between executing one, then the other, then the other. That is, unless you wait for one task to completely finish before making progress on the other one. With parallelism, think of a computer with multiple CPUs. When there are two tasks and two cores, they can both run in parallel. So behind the scenes, you have to remember there's a memory controller, a disk drive, a PCI bus, and a number of other shared resources. So while the tasks are running in parallel, they could still be limited by a common bottleneck. For example, if you're writing two large files at the same time, each file will be written at half the potential speed, or sometimes a bit less than that. And if there are more tasks than there are processors, you'll end up with both parallelism and concurrency, where the contention ratio is the number of concurrent tasks over the number of parallel processors. And whenever resources are shared in parallel, there will be contention. With blockchains, like Oasis Sapphire, you can submit transactions in parallel or concurrently, but ultimately they'll be serialized into a linear order in the block. So the blocks being mined only do one thing at a time, one after another in a sequence, and the block has a limit on how much it can do in one go. So bear that in mind that while transactions from the same account will be processed in order, there is no guarantee that your transactions will occur before or after transactions from another account. This can lead to unpredictability, or as we see on Ethereum, sandwich attacks and MEV. All transactions modify the database, and all writes to the database are serialized into a linear order, meaning transactions are atomic. Either it completes or it doesn't. If a transaction gets a different value from what it was expecting, it might fail. For example, if you wanted to do a token swap and the rate alters significantly, you would want to prevent yourself from executing a transaction outside of the accepted range. One of the aims when writing EVM contracts is to minimize the chance of failed transactions and to only make transactions when the global state needs to change. So we only need to make transactions when we need to modify values in the database. That means the more work we can do without modifying state will result in lower latency for the dApp. And that's because you don't need to wait for blocks to be mined. If you want to keep track of some metrics, an interesting one would be the ratio of view calls to the contract to the number of transactions committed to the blockchain versus the number of failed transactions compared to the average number of reads and writes per transaction. Now, view calls are free. That is, anything that's called via the ethcall JSON RPC method. And that doesn't modify state, it doesn't submit a transaction, so it doesn't cost gas. And a typical dApp may make 10 or even up to 100 view calls per transaction. So if you can make your dApp do more in view calls, which is possible because contracts can have confidential data, then you can scale further and use the throughput and compute power of all nodes, and only submit transactions when you need all the nodes to synchronize and agree on the same thing. So let's code. We're going to create an example contract which lets two people compare who has the higher number without revealing to each other what their number is. This is called the millionaire's problem. So here's my project, which is all set up from the previous video that I did. And that means that we have the deploy file, we have hard hat, we have the package JSON, and everything's ready for us to deploy onto Sapphire. So I'm going to start with creating the contract. So a new file, and let's call it number compare.sol. And the standard stuff we have to do is the SPDX license identifier. And I'm going to make this public domain under the Creative Commons public domain license. We say we want Solidity version 0.8 or above. And we define our contract. So in the constructor, I think we're going to need some kind of secret. So let's define a private variable called secret. And then in our constructor, we can say secret equals bytes 32. And then we're going to have to import the Sapphire library here. So import Oasis protocol / Sapphire contracts / Sapphire.sol. This will allow us to use the Sapphire library. So Sapphire.random bytes 32. So we're going to create 32 random bytes in the contract constructor, which is a private variable. The next thing we need to do is either person's going to encrypt their number, and they're going to give their encrypted numbers to the other person, and they can then use the comparison function. So we need a function for encryption, encrypt, a function for compare, and for the encryption function, let's take in some entropy from the person. So this is just some random data that they're going to put in, which obscures any sort of it verifies that the encrypted value is random rather than being deterministic, so nobody can guess what it is. Let's make this an external view function. So it's an external view function which requires no guess. And then we're going to return the nonce, which was used for encryption, and the ciphertext. So, and then in the compare function, we're going to take the outputs of the previous two encryptions. Let's call this external view. Let's return a bool. So I think this is going to return if A is greater than B. So with here, let's do bytes 32 nonce A and bytes memory A. So here we're taking the two encryption outputs and checking if A is bigger than B. So for encryption, we have to derive the nonce. So we set nonce equals, let's do bytes 32, and then we can use the random bytes function again, but this time we're going to mix in the entropy and the contract secret. And then ciphertext is going to be set to the result of encrypting the input number. So we do Sapphire encrypt with our secret and the nonce, and then let's encode the X variable, and we don't authenticate any additional data. So that's quite straightforward. Now in the compare function, we're going to want to decrypt the variables. So if we do, let's call these X and Y equals ABI.decode, because we encoded it previously, Sapphire.decrypt, the secret, and the nonce A, the ciphertext A, and no additional authenticated data, and the type of that is uint256. We can copy that. We can say B is minus B. So the decrypted values of A and B are X and Y. And we can say, let's return X is greater than Y. So this function doesn't require any gas. It doesn't leak the number. And of course, you need a bit more of a protocol around this to stop someone from brute forcing this, but this is really straightforward because it runs in a trusted execution environment. That means that the contract can encrypt data that only it can see, and it can be passed back securely to the contract itself by somebody else. Next, we're going to create a test for this. So if we create example.test.ts, and in this, we're going to deploy the contract, and then we're going to call the encrypt function twice with two different numbers, and then we're going to call the compare number function with the ciphertext and the nonces, which will return from the encryption function, which will tell us which number is bigger. So if we do import ethers from hardhat, because we're going to need ethers to deploy the contract. So describe, let's just say our contract. And the test we're making is it works. Very simple. So to deploy the contract, we need to make a factory. Let's put number compare. Yeah, that matches what we've got in here. And contract. Let's deploy this through the factory. And then wait for it to be deployed. So next, we're going to have to use some random data. So let's import random bytes from crypto.ethers. So if we say nonce A equals random bytes 32, random bytes 32 for the nonce B, and this matches the entropy parameter that we're passing into the encrypt function. And then the ciphertext A, along with or this entropy A rather, entropy B, then we're going to call the encrypt function, which will return both the nonce and the ciphertext. So let's say A equals await contract.encrypt and entropy A, and let's say person A has a $300 balance. Encrypt entropy B, let's say they have a $200 balance. So A is bigger than B, so that should return true. And then let's get the comparison results. So it's contract.compare, and A.nonce, and A.ciphertext, B.nonce, and B.ciphertext. And then let's log. Result is C. So this seems to match up. I think it should work. So if we then go into our terminal and we run the test, so we're expecting it to run true because A has a bigger balance than B. And if we go and set A to be $100 and B to be $200, then it will return false. And of course, we can see the encrypted values which are being returned by the contract are not decipherable by the user. So this means the contract can encrypt data that only it can see and only it can decrypt. So really, contracts on Sapphire act like a hardware security module, but it's in the cloud and it's programmable in Solidity. So that means if you can make your protocol work without requiring storage updates, then it's free for users after you've deployed it. And next, let's move on to an example that uses transactions rather than just view calls. So we're going to create a coupon system. Let's call it coupon.sol. And this coupon system is going to allow you to deposit into the contract, which will give you some ciphertext, which, along with the password, can be used to withdraw the value that you deposited without linking the deposit and withdrawal. Of course, if you deposit the same amount and withdraw the same amount, and it's a unique amount, then there's going to be linkage there. So let's start again with the SPDX license identifier. And let's make this public domain. For Solidity 0.8 or above, and import our Oasis protocol, Sapphire contracts, sapphire.sol, create contract coupon, and again we're going to need a private secret for the contract, which is set up in the constructor. Because we're going to be using encryption again. And next, we need some kind of structure to keep track of what's been spent, so to prevent double spends. So each coupon's kind of like a UTXO. So we call that points32 maps to bool, and so let's call these the nullifiers. So when a coupon's spent, you put the nullifier in there. So let's create the deposit function and create a password. And it's payable because we want to deposit some rows into there. And then we're going to derive a nonce programmatically, but it's a secret nonce based on the password using our contract secret. And then we're going to encrypt the value that's been deposited with the secret and the nonce. And we're using the password as extra authenticated data because it's bound to the nonce, but we're going to put it in there specifically. So we're going to use a secret, the nonce we created, encode message value, and then encode the password as the authenticated data. Let's put that onto a new line so it's easier to see. So here we have the ciphertext. We're encrypting the value, which is bound to the password and the contract secret. And we don't need an event to emit. Let's call this on deposit, the nonce, and the ciphertext. So let's emit this. So anybody that makes a deposit can then look at the transaction to see the on deposit event, but without knowing the password, you won't be able to withdraw this. So let's create the withdraw function. We have the password, the nonce, and the ciphertext. It's a transaction, so it's not payable, but it will pay you. And then what do we need to do? Let's create a nullifier. And this hash of the secret and the password, the other way around from the nonce, is going to be used to prevent double spends. So if we see require nullifiers password hash is false, so you can't spend this twice. And let's decrypt the value that's been passed in. And just remember that the values of encrypt and decrypt roughly mirror each other. So now we've got the plain text, we've got to get the value, so we ABI decode that. And then we set the nullifiers for this to true to prevent the double spend. And then we're going to send the value back to the sender. So that's whoever performed the withdrawal function is going to get the value sent back to them.